In a previous screencast, I talked all about the normal distribution. In this screencast, I'm going to talk to you about the standard normal distribution and the importance of standardizing and z-values. With today's computing tools, for example, Excel or others, it's not as important to know how to standardize and to use z-values, but nevertheless, it's really important to understand how we can use and derive these z-values. The standard normal distribution is a special case of the normal distribution, where the mean of the standard normal distribution is 0 and the variance is equal to 1. The standard deviation is also equal to 1, since it's the square root of the variance. By convention, the standard normal random variable is denoted as z, and that's really important. We denote it as capital Z and not as capital X. If you substituted mu equals 0 and variance equals 1 into the formula for the normal distribution, we would get this. So this function here is the standard normal distribution. Instead of capital F for a normal distribution, we represent the cumulative density as phi, this Greek letter phi, and that's the probability that our random variable z is less than or equal to a certain value. And I'll be talking a little bit more about this in a moment. There's a table of phi in your textbook. It's in Appendix A, and this was really useful back in the day before Excel was readily available. The standard normal distribution, again, the standard deviation is 1, the mean is 0, and what that means is that about 68% of the standard normal distribution lies between -1 and 1. That's within 1 standard deviation of the mean. 95% of the distribution lies between -2 and 2, within 2 standard deviations of the mean, and 99.7% lies within 3 standard deviations of the mean. Here's an example of the normal distribution. X is a normally distributed variable with mean equal 10 and standard deviation of 4. What's the probability that X is between 8 and 16? And in the previous screencast on the normal distribution, I showed you how you can use Excel formulas to do this, the norm.dist. Basically, what we're doing is we're taking capital F of 16 and we're subtracting capital F of 8. And that gave us our answer. 62% of the distribution lies between 8 and 16. Now what I'm going to show you next is how we would do these calculations before you could readily use these functions in Excel and other software tools. Any randomly distributed variable, we have two examples here, we can standardize or convert to the same playing field essentially. So we can convert the one on the left and the one on the right. They have different means and standard deviations. We can convert those through the standardization process to the standard normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1. And so this process is known as standardizing. This was useful when we didn't have computing tools because you could essentially level the playing field, convert everything to a standardized variable, and then in the back of your book or in various tables, you would have a cumulative distribution function that is published and readily available. So how do we standardize? We convert our normally distributed variable x to a standard normally distributed variable, capital Z. We do that through this formula. Z, our standard normal random variable, is equal to x minus mu over sigma. Essentially, all you do is you transform x into variable z. This transformation allows us to use a single source of information for the standard normal distribution, and this is in your textbook, Table 3 in Appendix A. With the advent of convenient computing tools, for example, functions built into Excel, Minitab, and MATLAB, this transformation is no longer as important, but it's really important that you still understand how this is done. Standardization is basically taking stretched and translocated distributions. We have this stretched clown on the top, we have this compressed clown on the bottom. They're both away from a mean of 0, and we standardize into a single common playing field. Now you saw previously that the cumulative distribution function capital F was just the probability that capital X, our random variable, is less than or equal to some value. We always integrate from -infinity to the x value. Now what we do for the standard normal distribution, we represent that as phi, capital Phi of Z, and that represents the probability that our random variable is less than a certain value for Z. And again, lowercase would just be that this is a certain value, like 1.5. Let's go back to our transformation equation here. Z equals x minus mu over sigma. We can answer questions like, what's the probability that x is less than or equal to some value? So what we're going to do is transform that into the z domain. We standardize. that's the same thing that probability of z is less than or equal to z. What you do is you take your x value, you subtract the mean, and you divide by sigma, and that is the transformed variable. And so now you have that in terms of z. In other words, we have a distribution here whose mean is 40, standard deviation is 0.3, and if you have a certain value of x, let's just say x equals 40.5, standardization tells us where on the standard normal distribution does that x correspond to. And so when we standardize, in this case, we would get z equals 40.5 minus 40 divided by 0.3, which is 1.67. That tells us that this x value in our normally distributed variable above corresponds to a z value that's equal to 1.67. Now they're exactly similar because remember, probability distributions, the area under the curve is always equal to 1. And so the probability less than or equal to x equals 40.5 would be that shaded region. That's going to be identically equal to the probability that z is less than or equal to 1.67 on the standard normal distribution. So it's just a similarity solution where we're converting something that's normally distributed into a standard normal variable. In the back of the book, you've got these cumulative standard normal distribution charts, and I've got a couple examples of how we will use this, but basically you've got your z value here, and your cumulative distributions make up the contents of the table. As you get to really high z values, you see that the cumulative distribution, it always starts from the left. The cumulative distribution approaches 1. Let's go through an example. What is the probability that a result will be less than 39.8? We've got a distribution where the mean is 40, sigma equals 0.3, and we're assuming this is a randomly distributed variable. So in other words, we're trying to find what's the probability that x is less than 39.8. That would correspond to about that shaded region. And we're going to standardize this. We want to see 39.8. What z value does that correspond to? And the probability is going to be the same because the area underneath this curve is always equal to 1. So that's what we're trying to do. 39.8 corresponds to what z value? And the probability that x is less than 39.8 would be the probability that z is less than that z value. So the probability that x will be less than some value x can be given by the probability that z is less than x minus mu over sigma. So this is our standardization. When we do that, we get the probability that x is less than 39.8 is the probability that z is less than negative 0.67. That's the same as the cumulative distribution function for the standard normal distribution phi. We can then go to the cumulative standard normal distribution table, table 3 in your book, and we can determine the probability of this occurring. Here I've got the table, and I have a z value of negative 0.67. We can go down here. We have the third column over is negative 0.07 in the hundredths place, so I go down here, and where we get negative 0.67, that's a probability of about 251. That means the probability that any x value be less than 39.8 is equal to 0.251.